Let me quickly remind you, we have an exam coming up on Tuesday. This is November 2nd. The room for the exam will be in 1511. And the way the exam will start is you'll have a few manual problems. And by a manual problem, I mean problems you have to just work out on a piece of paper yourself by hand without a computer. And then most of the exam will be online. So what you'll do is you just type up your work, you write up your work, and submit it at the end. So that's what you will do. Now, this room 511, there's two rooms that are right next to each other. One of the rooms is a regular lecture room. The other room is a room with computers. So if you do not want to bring your own computer, there will be a room next to it that will have computers in it. And so you'll be able to, we'll put the class between the two rooms. Now, I should, of course, say that the exam is still online. Even though you're taking it in person, the exam is still online. I think this is nice just in case, let's say something happens and you suddenly cannot show up. Like, let's say you're on the train and then the train stops moving and you have to take the exam. And now you cannot show up to take the exam. In that case, you can still take the exam. You can still take the exam. Now, everyone is expected to show up, but if something happens beyond your control and you're not able to show up, you can still take the exam. You can still take the exam online, and then just like on the first exam, just email in your work. So it's not like you get locked out of the exam. So that's one of the reasons why I'm doing it as an online exam, and also because it gets automatically graded for you. So when you submit it in, you will automatically get the grade very soon afterwards, and then I'll just do the manual problems and then add that on top of the grade that you already get. Now, I will say more details about the exam, but for now I want to get to the lecture. This is just a reminder that we have an upcoming exam. Yeah, so if you've done your IDs, your ID should be updated. You can then get into the building, and the exam is at 5 p.m. I'll give you more details when it becomes appropriate. For now, this is just a reminder that we have an upcoming exam. Also, there is an extra credit class on Monday that we did. It's already posted. And then we'll have a problem class tomorrow night. I'll send you the details when I can find a convenient time to do it, but it'll be closer towards night, as it usually is. If you want to come in live, I'll go over more problems. But let's get to the actual lecture. So what we're going to be talking about is this. So suppose you have a linear map. Yes, we will have the question that was the last 20% of the last test as well. That will be one of the manual questions you have to do. So that will be part of it as well. So suppose you have a linear map. The problem is you want to find a basis to use so that the matrix that represents this linear map is as simple as possible. Now, of course, we have to clarify what we mean by as simple as possible, but let me just show you an example for you of what we're trying to say. So suppose you have the following linear map. So this is on two-dimensional space, you have a linear map, and f of x is given by this matrix, 5, -3, -6, 2, like so. Now, if you pick the following basis, so here you'll have two basis vectors because you're in two-dimensional space. But if you pick the following two basis vectors, so the first basis vector is going to be -1, 1, and the other basis vector you're going to use will be 1, 2. So if this is what you pick for your basis, then let's see what happens when you apply f to the linear when you apply the linear map to these basis vectors. So if you do f applied to x1, you will get 5, -3, -6, 2 multiplied by -1, 1. And if you do that, a calculation will show you that you get -8 over here, and you also get 8 over there. And if you do f applied to x2, the other basis vector, you would get this, 5, -3, -6, 2, and then you have to do matrix multiplication with the vector 1, 2. And if you do that multiplication, you will get that it's equal to -1, -2. So now that you've done this, the question is, how do you write this in terms of the basis vectors? So anytime you want to find the matrix that represents the linear map, we have to apply the linear map to the basis vectors, and then we have to take the images. So these are the images of the basis vectors under the action of the linear map, and then express them back in the coordinates with respect to the basis that we're using. So if you look at this, you will notice that x1 originally was -1 and 8, and the output vector is -8, 8. So it's just a multiple of 8 of what it was before. So the correct coefficient here would be 8, and this one would be 0. And this one, f of x2, you can see the vector 1, 2 got sent to the negative of itself. So therefore, the correct coefficient here would be -1, and this is just, no, let me take that back. So this one would be 0, and this one would be -1. So that would be the way you would write that. So because of that, it means that the matrix, so the matrix that represents this linear map with respect to this basis, if you write it out, it would be 8, 0, 0, -1, because you have to write these as columns. So you write this as a column, and then you write this one as a column. There it is. So you can see this is the matrix that represents the linear map. And this is a much simpler matrix. So as you can see, this matrix with respect to this basis is much simpler than the original matrix, which was with respect to the standard basis. So if you use the standard basis to represent this linear map, then this would be the matrix that you're using. But if you're using this basis instead, if these are the basis vectors that you use, that you choose, that you're chosen in this clever way, then the matrix that represents the linear map would look like this. And it's a lot simpler to work with. It's a lot simpler to work with for many reasons. One of the reasons is this. So you would say that if x is a vector, so let's suppose you have a vector, and then you write your vector in terms of the basis vector. So you write it as ax1, let's suppose, plus bx2, then it becomes very easy to find the image of this vector. You do not have to do any kind of matrix multiplication. F applied to that vector would be F applied to ax1 plus bx1. But because F is a linear map, it means we can write it like this: F of x1 plus b of f of x2. And we just said that x1 gets sent to 8x1 and x2 gets sent to negative x2. So we can immediately just replace these by 8x1, and we can immediately replace this by negative x2. And you can see just how convenient this is. It's very simple to, if this is the basis that you're using, it is very easy to study this linear map. If you have a vector and this is the way the vector gets written in terms of the basis vectors, if you want to determine the image of this vector, you will notice all what happens is the coefficients, they stay essentially the same. This one gets multiplied by a factor of 8, whereas this one becomes a negative number. But other than that, everything stays the same. There's no complicated way of combining these numbers whatsoever. So by using this basis, it's so much easier to study this linear map. It's also, as you can see, when the matrix is written in this kind of in a diagonal way, it's also very easy to find its determinant. You just multiply these two numbers. Like in this case, it's not a big deal because this is a 2 by 2 matrix, so it's easy to find the determinant of this matrix. But if you have a larger matrix, for example, if it's a diagonal matrix, it's very easy to work with. It's also very easy to find the inverse, for example. The inverse of a diagonal matrix, all you have to do is take the inverse of these two numbers. It's very easy to take the inverse of a diagonal matrix. It's not easy to take the inverse of a matrix in general. It's a tedious calculation that you have to do. So for all sorts of reasons, if you use a cleverly chosen basis, you can greatly simplify the computations that one has to do with the linear map. So the point here is that if you can choose a cleverly chosen basis, you can greatly simplify calculations involving the linear map. And that's really what we're trying to do. And we saw a little bit about this last week. Last week, we did this very detailed example where we were trying to study rotations in three-dimensional space, and we chose a basis that made the study of the linear map a lot simpler. And we were able to solve the problem with respect to that basis and understand what the correct rotation matrix was. So this is somewhat the same idea, that you're trying to find a convenient basis. Now, if you look at what's going on here, basically what's happening is, if you look at this, you will notice that f of x1 essentially goes back to itself. You're not using any x2. That it's not included. It's basically being mapped to itself. Not exactly, there's a multiple here, but it's being essentially mapped to itself. And f of x2, that's the other basis vector. F of x2 is being mapped to, so this is not present, it gets mapped almost to itself. So you can see it's negative x2. And the same thing happened when we talked about rotations. We saw that if you're rotating something, if you're doing a rotation, around the vector by an angle of theta, if one of the vectors you pick is the axis of rotation vector itself. We saw it's just itself. It's kind of the same idea that if you want to talk about rotations around an arbitrary vector in space, if one of the vectors in the basis is chosen to be the axis of rotation vector, then you can see the rotation around itself, it's just itself. The vector, in this case, it's being sent exactly to itself. The vector is not moving. But more generally, you could allow the possibility that maybe the vector is not exactly being mapped to itself, but it's being mapped to a multiple of itself. And this is going to be the motivation for the definition that we're about to write down. So I'm going to go ahead and clear the board, and we're going to describe something called an eigenvalue. An eigenvalue is, it's the numbers that come up in this kind of a way. We'll make it more precise in the definition. So today, so the plan is this. Today, we're going to talk about this thing called eigenvalues. That's what we're going to talk about today. And then on Thursday, we will then use our knowledge of eigenvalues to determine these convenient bases. How we will talk about how you can find such a basis. Like in this particular example, I'm not showing you how I found this basis. I'm just showing you that it works. But we will discuss the procedure and various theorems about how you know or how you find such a basis for a linear map. But today we'll just talk about these numbers that come up. So let's go ahead and make this definition. This is sort of the main definition for the day. So let A, so you can say this. You can say let A be a matrix, an n by n matrix, which you can think of as a linear map. We always say that you often want to think of matrices as linear maps. You have a linear map from Rn to Rn. That's the way you can think of a matrix. It acts like a linear map. So if you have a matrix, or if you prefer to say a linear map, an eigenvalue is a real number. I mean, it could be complex, but we're not going to talk about that. We're not really going to put a lot of emphasis here. It's a real number, and usually people use the notation lambda. I'm not sure why people decided to adopt this notation for the notation of an eigenvalue, but that's became sort of the standard notation. So this is a Greek letter. It makes an L sound, lambda. So it is a real number, lambda. So this is, of course, a real number. So it's a scalar. It's not a vector. It's a scalar. So it is a real number that has the following property. And again, it could be a complex number. So complex means you could also allow imaginary numbers as well. But it's not something we'll put a lot of emphasis on. I'm just going to mention that because sometimes people do talk about complex eigenvalues as well, though we're not really going to be doing much with them. So it is it's a real number which has the property that you can find a non-zero vector x so that ax is equal to lambda x. Or if you prefer, you can also think of it like this. This is another way how you can think of it. You can also think of it like this. You can also say that a of x, because a is, in a way, a linear map as well. The linear map applied to the vector, it's not exactly the vector back to what it was, but it's a multiple of itself. That's what it's saying. So you can, a more sophisticated way to say it, you can say the linear map maps, the matrix A, viewed as a linear map, maps X almost to itself. In other words, a multiple of itself, and that ratio and that constant multiple is called the eigenvalue. Eigenvalue. That's how you can think about it. We do say non-zero vector because if you allow zero vectors, it's not very interesting. This is always true because the zero vector always gets mapped to itself. A of the zero vector is always equal to the zero vector. And then you can put anything you want for lambda. Then anything, because 0 times anything will always be 0. So it's not a very interesting condition if you allow 0 vectors. And also, whenever you talk about basis vectors never contain the 0 vector anyway. So you have to make sure you're looking for non-zero vectors. So the question here is, how does one find the eigenvalue? And sometimes you have more than one. So how does one find the eigenvalue? So here's a proposition. And this proposition is going to tell you how to find the eigenvalues. To calculate the eigenvalues of a matrix, or if you prefer, equivalently, a linear map, you need to solve the following equation. So the equation that you need to solve is this. It's the determinant of A minus lambda times the identity matrix. The n by n identity matrix. You set that equal to 0, and then you solve this equation. Or in some books, depending on what book you look at or what sources you look at, they write it in the reverse order. They write the determinant of lambda in minus a is equal to 0. It's not that big of a deal because if you factor out a negative sign out of a determinant, it will always be plus or minus. It depends on whether or not the dimension number is even or odd, as we did on that homework problem. So it does not really change the equation because if you put plus or minus on the 0, it's not changing anything. So in some places they write it like this. And this is called, this equation turns out being a polynomial equation in terms of lambda, and is a polynomial of degree n. When we do some examples, you will see why it's a polynomial. Basically, because you're calculating a determinant. And when you calculate the determinant, you have to look at all possible multiplications. And when you end up multiplying all possible combinations involving lambda, you're going to get n factors of lambda, which is going to give you a polynomial equation. But this is going to be a polynomial, and it is typically called, it is commonly called the characteristic polynomial. That's the name they refer to that. So what I'm thinking to do is let's actually do some calculations first, and then we will justify this. So let's do some calculations first, and then justify why this is the correct equation. Actually, quite easy to show that. That's why I'm calling it a proposition. It does not take a lot of work to derive. But let's first do some examples so that we at least understand how this works before we justify why this is the correct equation. So let's start with the example that we just did earlier. So the example that we just did was the matrix, was this matrix. It was the matrix 5, -3, -6, and 2. And then we're going to find the eigenvalues. So what we're going to do is we're going to find the eigenvalues of this matrix. And then the 2 by 2 identity matrix is this, 1, 0, 0, 1. And the characteristic polynomial is you have to take the determinant of the matrix minus lambda times the 2 by 2 identity matrix. So that would be the determinant. And now you do your calculation. You subtract from A, you subtract lambda times the identity. Now, you will notice that the identity matrix only has ones on the diagonal, and it is 0 everywhere else. So you will multiply lambda only on the diagonal, and then you would subtract those numbers away from that. So if you do that, if you do this correctly, it's going to look like this. You're going to have 5 minus lambda, -3, -6, and you're going to have 2 minus lambda. That's what you get. So basically, you're just subtracting lambda on the diagonal. That's what you're doing. Everything else stays the same. The matrix, it's the matrix that you have in the beginning, 5, -3, -6, 2, which is right over here. It stays exactly the same. And then you subtract lambda. But since this is the identity matrix, the lambda will only be on the diagonal. So you subtract the lambda away from the diagonal, and this is what you get. And now when it's set up this way, you can very easily calculate the determinant of this. So the determinant here is going to be equal to 5 minus lambda multiplied by 2 minus lambda. And then we will have minus -3, -6. And if we multiply all of this out, we would get 10 minus 7 lambda plus lambda squared. And then we would get -18. And if we just write it in the correct order from highest power to smallest power, this is lambda squared minus 7 lambda, then this is -8. And at this point, you can factor this. So this is lambda minus 8, and then this is lambda plus 1. And after you factor it, you can then go ahead and find the roots. So you can now say that the roots of this polynomial equation of degree 2 are, so these are the following roots. So the roots here are going to be equal to lambda is equal to 8, and then lambda is equal to -1. You could even give these names. You can call this like lambda 1 and lambda 2, just to indicate that you have two different roots. And if you're thinking about which one should be the first one and which one should be the second one, it does not really make much of a difference. Maybe sometimes people like to put them in ascending order. So maybe you call this lambda 1 because that's the smallest one, and then lambda 2, that's the next one. But it really does not make much of a point here. You're not going to lose any kind of points depending on which one you call lambda 2, as long as you find them in the correct way. And this is the way you find this. And you will notice this is a polynomial. This over here, this is a polynomial equation of degree 2. This is the quadratic. And that's not a surprise, because if you look at the calculation, when you're finding the determinant on a very simple level is you have to look at all possible ways of multiplying numbers in this column with numbers in that column. So lambda gets multiplied with lambda, and that's the reason why you get lambda squared. And if you had a 3 by 3 determinant, which we will do, you have 3 products of lambda. So that's why you get a lambda cubed. And that's why you're getting a polynomial equation. So this is the way you find it. Now, of course, you do have a calculator for doing this as well. And let me just show you the way you would do this on Mathematica, just so you know. You will, of course, be permitted to use a calculator if you have to, but it's also important to understand what an eigenvalue is, because sometimes you have these conceptual problems where you have to make sure that you have an understanding of an eigenvalue so you can use it in a particular problem. But if you're just doing a purely computational problem, and there's not much thinking involved, then the only thing you have to do is you just type eigenvalues and you type in the example that we just did. So it would be 5, -3, and it would be 6, -2. So you would just type that in, and it gives you the eigenvalue. So it calls this one lambda 1, it calls that one lambda 2. The order in which you call them, the name that you put them is not important here, but these would be the eigenvalues. Now, for the time being, you ignore this. This is something called eigenvectors. We're not talking about these today. We will talk about those tomorrow. But for today, we're only talking about the eigenvalues. Eigenvalues are numbers. And basically, to put it very simple, the eigenvectors are the vectors. So we said an eigenvalue, it's a number for which the matrix maps a vector to a multiple of itself. So when you're saying over here that 8 is an eigenvalue, you're saying that there is an eigenvector out there that when you apply the matrix to, it gets mapped to a multiple of itself. So what this is telling you that if you use this vector, so this is lambda 1, this is v1. So if you use this as your vector, if you apply this matrix, if you let this matrix act on this vector, you will get a multiple of 8. You will get -8, 8. So it's also telling you how to find those particular vectors. But we'll make a comment about that because it is a little bit trickier with the vectors. There's a lot more to be said about that than what just Mathematica says alone. And this is where going to be one of those instances where having a mathematical understanding will be quite helpful here. Very often when people just look at this particular answer coming from math, they often get the calculations wrong because there's actually a lot more vectors than what you're seeing from Mathematica. It's just describing one possible basis that you can use. But we'll make a comment about that on Thursday. For the time being, we're only focusing on the eigenvalue part of the problem. So let's do another calculation. Let's do a 3x3 calculation. Let's do something that involves a 3-dimensional matrix. So this time, let's change the problem a little bit. So we'll get rid of this, and this time we will have the following. So this time the matrix is going to be, we're going to use the following matrix. We're going to use the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0. That's going to be the matrix. And this time we have to use the 3x3 identity. So we're going to have to use this one, which is quite interesting because, as you can see, it's sort of the complete opposite of this one. This one is zeros on the diagonals, ones everywhere else. Here you have ones on the diagonal and zeros everywhere else. And as before, in order to find the eigenvalues, what we have to do is we have to calculate the determinant of A minus lambda times the 3x3 identity matrix. So this would be the determinant, and the matrix here that we're going to use is very simply, it would be exactly these numbers, and then you would subtract the lambdas across the diagonal. So you would have something that looks like this. So you would have negative lambda, negative lambda, negative lambda, and then you have ones everywhere else. That's the way the matrix is going to look like when you subtract them. And now you have to find the determinant of a 3 by 3 matrix. So there's all sorts of ways you can do it. Let's just do it on Mathematica to save time. Now, I mean, one way you can do it, of course, is you can break it up into these 3 columns and then look at all possible ways you could multiply this. Lambda times negative lambda times negative lambda times negative lambda, that would be negative lambda cubed. And then you have to determine whether that's a positive or negative permutation. Then you can do lambda times 1 times, I mean, things like that. Actually, let's do it by hand. I think it's just an excuse to do this, practice doing this by hand. So we can have negative lambda times negative lambda times negative lambda, and the permutation here that we're using is 1, 2, 3. We're picking the first number in the first column, the second number in the second column, third number in the third column. The other way we can do this is we can do lambda negative lambda times 1 times negative lambda. In this way, the way we're doing it is we're taking the first number, that first number, third number, no, that's a mistake. Let me try that again. So that's negative lambda times 1 times 1. And this way we're taking the first number in the first column, we're taking the third number, and then the second number. Okay, so what that means is 1, 3, 2. So we're taking the first number here, the third number, this is the third number, and then the second number. We can do negative lambda multiplied by, the other one would be 1 times negative lambda times 1. And this one is 3, 2, 1. We can have also 1 multiplied by 1 multiplied by minus lambda. In this case, we are doing the third number multiplied by the first number and then multiplied. Okay, that also does not work. Let me actually do it like this. 1, 3, 2, 1, 1, 2, 3, 1, 3, 2, 3, 2, 1, 3, 1, 2.
Professor, the last one isn't it 2, 3, 1?
3, and we have 2, 3, 1. Let's do it like that. And then that would make it easier to see. So let's try that again. So 3 goes first, so that's 1. So 3 goes first. That would be 1. And then the first number is 1, and then we have the second number, which is 1. And then we have the second number, which is 1. Then we have the first number, which is 1. Then we have the third number, which is minus lambda. Then we have the second number, which is 1. Then we have the third number. And then we have the first number, like that. So is that okay? Anyone have any questions on this? I mean, you can see it's tedious. That's why we have calculators. And now you just have to determine whether or not these are even or odd permutations. This is a positive sign because it's in the correct order. This one, let's see. This one is going to be with a negative sign because you have to do 1 flip. This one is going to be with a negative sign. You have to do 1 flip. This one will be with a positive sign because you have to do 2 flips. This one is going to be with a negative sign because you have to do 1 flip. And this one has to be with a positive sign. It's a nice fact to know that the amount of positive signs and the amount of negative signs is going to be the same. Okay, and then you multiply these out. So if you do that, you would get negative lambda cubed. So multiply them out with the correct signs. This would be plus lambda. This would be plus lambda. This would be plus 1 then that would be plus lambda, and that would be plus 1. So that is what happens when we do that. So we end up with minus lambda cubed plus 3 lambda plus 2. Okay, that is what we get when we do that. Let me just check that this is actually correct before I do anything. I mean, we really should have done it on a calculator earlier, but the point here was to the whole point here was to actually was to do this by hand carefully. And now you can factor out. Now what you can do is you have to factor this. And factoring polynomials is not easy at all. Sometimes they have very complicated roots. This one, fortunately, has a simple factorization. You can do negative lambda cubed plus 2 lambda plus lambda plus 2. Let's see if this works. Let's see if this works. So you can write it like this. Then you would have to factor out a lambda. And then you would have negative lambda squared plus 2, and then plus lambda plus 2. So this is not, yeah, this does not work, as you can see. You cannot factor that out. So we have to look for ways to factor this thing. Now, you are, of course, permitted to you are permitted to use a calculator to do this. So let me just make this comment here. Factoring polynomials of degree 3 and above is generally very hard, okay? Because it's the problem, it's essentially the problem of finding roots. So the way this polynomial factors, instead of trying to spend time on trying to figure out how this polynomial factors, we'll just do it on Mathematica. So the way this polynomial factors is in the following way. It will factor as lambda minus 2, and then it will factor as lambda plus 1 squared. So that's the way the polynomial factors. If you're wondering how you're getting this, sometimes the way you do it is you can sometimes guess a root. So if you look at this polynomial, you can see that negative 1 works, because if you put negative 1 in here, you get a 0. And since you know that negative 1 is a root, you can then use long division to divide that out. So these are the kinds of things you can do. But they're very tedious, and they take up a lot of time. And I really want to mainly focus on the idea behind it, rather than just doing some tedious algebra computations. But once you have the factorization, once you find it, which again, in general, that's not easy to do, but once you find the factorization, in this case, the problem was intentionally set up to have very simple eigenvalues. But once you find the factorization and you set it equal to 0, you would say, so there's 2 roots here. So there's 2 roots. So there are 2 roots to this polynomial equation, which are 2 and negative 1. But you should notice that negative 1, that the factor that gives the root of negative 1 is repeated twice. Okay, so you will notice that this factor is being repeated twice. So it's true, you do have a polynomial of degree 3, and as they teach you, if you have a polynomial of degree 3, it usually has 3 roots. But sometimes it might happen that one of the factors are identical, and then when one of the factors are identical, both of those roots are really the same root, but you write it twice. So you would typically write it like this. You would write it as, if you would write your 3 roots in the following way. So you would probably write it in the following way. You would write that lambda 2 is maybe 2, and then lambda 1 is -1, and lambda 3 is -1. So you're repeating these twice. You're repeating these twice to symbolize that the polynomial has a repeated factor in it. So in actuality, you only have 2 eigenvalues, 2 and -1. But 2 of these eigenvalues, you would say that the -1 has a multiplicity factor of 2 because of that. So that's often the way that you write it. So if you do have repetitions in the factors, then you just write the eigenvalue that many times. So this is a more tedious calculation. You can already see immediately by just going from a 2x2 matrix to a 3x3 matrix just how much more difficult this became. It's usually a good idea to mention the multiplicity for each eigenvalue so that people know that you have a linear map with repeating eigenvalues. Sometimes that matters in certain cases, knowing that kind of information. So now let's explain why this equation works. Now that we did the examples, let's explain the justification for that equation. So fortunately, this is a simple derivation. And the way you do it is an eigenvalue, by definition, is a non-zero vector so that ax is equal to lambda x. That's the definition of an eigenvalue. Back to the definition, that's what an eigenvalue is. It is a non-zero vector. So an eigenvalue, it is a number with the property that you can find a non-zero vector so that ax is equal to lambda x. And now when it's written like this, you're going to bring this over to the other side. You're going to write this as ax minus lambda x. And then this is, of course, you have to be careful. This is not the number 0. This is the vector 0. So maybe you kind of write it like that too. Sometimes people get sloppy and they just write it like this. But you should understand that this is, of course, a vector, the vector 0. Now, here's the part you have to be very careful with. At this point, you might be tempted to factor this out. You might be tempted to write this. The problem is you cannot do that because A is a matrix and lambda is a scalar, and it makes no sense to subtract the scalar from the matrix. These are 2 different things. Matrix number, they cannot be combined together. So this does not work. However, you can just introduce the identity matrix into the middle of the problem. You can just do this. You could do minus lambda, and then you can just introduce the identity matrix. Like that. You can introduce the identity matrix because the identity matrix acting on the vector is just the vector itself. And now that you introduce the identity matrix, now it's permitted to factor everything out because now factoring makes sense. Because this is a matrix, this is a matrix, they can be subtracted together in this, and now it works. And we want this to be equal to 0. So since we want a non-zero vector, so let me write it over here. So since we want a non-zero vector, x, it means the matrix in the parentheses is non-invertible. Why? Well, it basically has to do with this. You have a minus lambda I times x is equal to 0. If the matrix is invertible, you can bring the matrix over to the other side, and you will be able to say that x is equal to a minus lambda I inverse times the 0 vector. And then you would get that x is equal to 0 because whatever this matrix is, when you multiply it by the 0 vector, it's just the 0 vector. And you're getting that x has to be the 0 vector. But you want a non-zero vector. And in order to get a non-zero vector, it must be the case that this matrix inside this bracket must be a non-invertible matrix. Because otherwise, if it's an invertible matrix, the vector is forced to be 0. So therefore, the matrix is not invertible. So since a minus lambda x is not invertible, it means its determinant is 0. So the determinant of it must be equal to 0. And now it's the number 0, not the vector 0. So this was the vector 0, this is the number 0. And that justifies this proposition. That's the justification for that proposition. Now, let me show you an interesting exercise that you can do, which is not difficult, but it's a nice fact to know about 2x2 matrices. So here is a nice fact about 2x2 matrices that is helpful to know. A lot of questions on exams and things like that, because they're trying to keep the problem simple, they usually stick to 2x2 matrices. And if you have a 2x2 matrix, this is like a nice fact to know. That if A is a 2x2 matrix, then if you calculate the determinant of A minus lambda identity, if you calculate it, you will get the following polynomial. You will get lambda squared minus the trace of A times lambda, and then plus the determinant of A. So what we're saying is that if A is the matrix, let's call it A, B, C, D, then to remind you, the trace of the matrix is the sum of the numbers on the diagonal. So that would be A plus D. And the determinant of the matrix would be, as you know, AD minus BC. This is actually very easy to justify. All you do is you take this matrix, you put it inside the determinant, you multiply everything out, and when you factor things, you will notice that the number in front of the lambda is A plus D, which is, by the way, the trace of the matrix. That's called the trace of the matrix. And the number by itself will be the determinant of the matrix. So such formulas, if you have a 3x3 determinant, maybe I can mention this. If you have a 3x3 you have actually something similar. So if A is a 3 by 3 matrix, then if you calculate the determinant, A minus lambda times the identity, you will get, it will be negative lambda cubed. Then it would be plus the trace of A lambda squared. Then it would be some mysterious number that there's no simple description for. Then it will be minus something lambda. And then at the end, you will have plus the determinant of the matrix. So you have a very similar looking formula like the one for 2 by 2 matrices, but the issue is the number in front of the lambda does not have a simple description for it. Like here, the number in front of the lambda is just the trace, and the number by itself is the determinant. For a 3 by 3 determinant, for a 3 by 3 matrix, you have something similar. The first number you're going to come across will again be the trace, which is just the number on the diagonal, and the number at the end will be the determinant. But this one does not have the same simple description as the other one. So because of that, the only simple formula that exists is the one for 2 by 2 matrices. For 3 by 3 matrices, you can kind of use this as like a partial check to maybe see if you're somewhat on the right track. So this one you'll be able to justify yourself. I'll do that during the problem class, where you'll be able to we'll go over why this one works. And now let's do one more example. And in this example that we're going to do, we'll actually also talk about the fact that eigenvalues could be complex numbers. It's not something we'll often come often around in this class. Most of our examples will have real eigenvalues, but it's just something that you should know in general. So let's consider this. Let's do an example involving rotation matrices, R theta. So this is so the rotation matrix. This is the 2 by 2 rotation matrix, cosine theta, sine theta, like this, and then it's minus sine theta, cosine theta. And the problem is going to be this. Determine the angles for which this rotation matrix has real eigenvalues, and justify this fact geometrically. And then I think this is the more interesting part of the problem, to see if we can justify the algebraic answer by geometrically visualizing what this linear map is doing. So this is a rotation matrix. If we want to find the eigenvalues, we have to do r theta minus lambda I. And we just said it's going to be lambda squared minus the trace of our matrix, and then plus the determinant of our matrix. Now, when we put the numbers in here, this is lambda squared. The trace will be the numbers on the diagonal. So here the trace would be cosine theta plus cosine theta. So that would be minus 2 cosine theta times lambda, and then plus the determinant. And the determinant is 1. There's different ways you can see why it's 1. You can just algebraically see it's cosine squared plus sine squared, or the geometric explanation here that we talked about. The determinant is the distortion factor, the spatial distortion factor. Rotations are orientation preserving, and they do not distort images. So because of that, the determinant has to be 1, because the images do not, the size of the image never changes. It's just being rotated. So that's why it's 1. And now you can find the eigenvalues. You will say that the eigenvalues, that lambda 1 and lambda 2, there's two of them, you would find them in the following way. It would be equal to, so it would be equal to, you use the quadratic formula. So you use the quadratic formula, you know the quadratic formula. It's the middle number. So it's the negative of the middle number 2 cosine theta. And then you have plus or minus the square root of the middle number squared. So 2 cosine theta squared. And then minus 4 times the numbers on the outside. So in this case, it's just 4, and everything gets divided by 2. So this is equal to 2 cosine theta plus or minus. You can factor out a 4. So the point here is 2 squared is 4, and you already have a 4. So you factor out a 4 out of the square root. But when you factor out a 4 out of a square root, it becomes a 2. So that will leave us with cosine squared theta minus 1, and then everything gets divided by 2. And so the eigenvalues, the two eigenvalues that we're going to get, are going to be cosine theta, and then it'll be plus or minus the square root of cosine squared theta minus 1. But here's the issue with this. So usually, for most angles, if you take the cosine of an angle, a cosine of theta, it's always a number that for most angles is always smaller than 1 in absolute value. You know that the cosine of the angle never gets too big. It's always a number between -1 and 1. And so for most angles, lambda, the eigenvalues would be complex, or you can say imaginary numbers. Okay? But there's two special angles where you have real eigenvalues. So the special angles where you have real eigenvalues happen when cosine of theta is equal to, well, let's say it like this, where cosine of theta squared is equal to 1. It's when it becomes a maximum possible number, because you're subtracting 1 from it. So the maximum this can ever get is 1. So that's when you have real eigenvalues. You have the square root of 1 minus 1, which is the square root of 0. So that's what happens when you have cosine squared of theta is equal to 1. So what we're saying is the angles where you have real eigenvalues is when the cosine of theta will either be plus or minus 1. You have to be careful here. It's really plus or minus 1 because the number is being squared. And what angles are those? So the angles are, you can have the 0 angle, you can have pi, and that is it. So these are the two angles. So these are the two angles for which this is the case. We're not including 2 pi because rotating around by 2 pi is the same thing as rotating by an angle of 0, so there's no need to include that. So these are the two special angles. These are the two special angles for which the rotation matrix has real eigenvalues. All other angles, the eigenvalues are complex numbers. That means you have to include the imaginary unit in there. And let's see if this makes sense geometrically. Let's see if we can justify this on a geometric level. I mean, this is what the algebra says, but let's see if we can use our geometric thinking to justify why this answer makes sense. So you have to think what this is doing algebraically. This is a rotation matrix. This is rotating vectors in the plane. This is a two-dimensional transformation. It's a two-dimensional transformation in the plane. So what this is doing is that if you have, so this is your plane R2, and you have some kind of vector, call this vector X. And then you rotate this vector. So you rotate this vector by a certain amount, and this is now R theta of X. And it's being rotated by an angle of theta. Now, to be an eigenvalue, what does that mean? That means that R theta of X has to send the vector to itself. Well, not exactly to itself, but it has to send the vector to a multiple of itself. Now, think about this. What are the only angles that do this for you? It's either 0 or pi, because if you rotate something by 0, the vector that you start and the vector that you end are the exact same vector. But if you rotate something by pi, so this is X, if you rotate something by pi, then the vector points in the opposite direction, which is R theta of X, which is now, so it's an eigenvalue. It's going to be an eigenvalue of -1, because it's a multiple. It's the same vector, but it's a multiple of -1. It's pointing in the opposite direction. So when theta is equal to pi, then the eigenvalue is cosine of pi, which is -1, which makes sense geometrically. But the other vectors do not have that property. If you do a rotation by an angle of pi over 2, no matter what vector you pick, it will always be perpendicular to it. You will never have these two vectors be pointing, you will never have this vector, aligned in the same direction, or maybe opposite direction, but parallel. You will never have this vector be parallel with this one. As you can see, these two vectors are parallel, and these two vectors are parallel. And geometrically, it makes sense that the only angles that you can use where you have real eigenvalues, where you can actually find real vectors that do that for you, are the ones where theta is either 0 or pi. All of the other choices of theta that are not these two special angles will send a vector that is like, I mean, you can see this, that if you just draw this vector, and if you draw this line, so this over here, this line represents all of the vectors that are parallel to it. If this vector is being rotated, no matter how you rotate it, it will never point in the, it will never be on that line, except in the special case where it's either this or this. That will be the only two special angles for which that happens. And then you can see why that agrees with the algebra of what we're doing over here. So we'll finish here. We said everything we wanted to say about eigenvalues. Again, you are permitted to calculate eigenvalues on the exam if you have to. As you know, I generally try to come up with problems that do not require any intense computation. I mean, I could ask you a geometric problem. I can give you a linear map that has a geometric meaning to it, and then ask you what are the eigenvalues and things like that. Then you have to use your geometric understanding to determine something like that. And then you cannot really do it on a calculator. But if you are doing a problem that is computationally intensive and you have to calculate something out, then you will be permitted to just open up your browser to Mathematica, type in the matrix, get the calculation, and then when you hand in your work on the exam, when you actually write out your work to submit it, you will just write on the exam that this was calculated on using a computer, and then you just proceed with the rest of the problem. So we'll finish here. As I said, tomorrow we'll have a problem solving class we'll go over. I still have to add just a few more problems to that list. I'm thinking about having a problem class tomorrow for Wednesday, and maybe another problem class maybe on something like Saturday, and then one more extra credit class right before this exam comes up. And the exam is open book, except for the manual part. So the first part of the exam, in fact, I'll tell you right now what it is while we have time. So there will be, so the manual part of the exam, you're going to have 3 questions that you have to do manually. So the first question will ask, you will have a 3x3 matrix, and you have to find the inverse by hand, right? Not by Mathematica. That would not be a very interesting problem. Then part 2 would be, you will multiply the 2 matrices in part 1 and show they multiply into the identity matrix. You will actually do matrix multiplication. You will show that you know how to do matrix multiplication. And then the third part of the question will be, you will calculate the determinant of this matrix. And you can use any method you want to do this. You can use row reduction to find the determinant. In fact, that would probably be the easiest way of finding the determinant, because since you're using row reduction to find the inverse anyway, maybe you can just take advantage of your work and use it to find the determinant. So the first 2 problems, this will be plus 20 points added to exam 1. This is for exam 1. And then this will be plus 10 points. This is going to be added to exam 2. So that's going to be what you would expect. So when you come in to take the exam, I will put a matrix on the board. In fact, I will also say this, the matrix, the final answer for the inverse will not involve fractions. So I will try to set up the problem so it comes out to be as smooth as possible so you do not have to deal with fractions. It is possible that you might have to use fractions in the middle steps, but on the final answer, I'm sure that when you've done a lot of these row reduction problems, you probably notice that sometimes in the intermediate steps you have to use fractions, but in the end everything sort of cancels away and you're left with something that is a nice number. And also, because the matrix has an inverse, the determinant has to be something that's non-zero. So you know you're going to get something that's non-zero. And that's going to be the way the manual part of the exam will go. I think that maybe 15, 20 minutes will be enough to do that, especially because all of these problems are intentionally designed to be quick. And also, they're all very much related to each other. So you'll just do that yourself without a calculator. You'll hand that in, and then you'll just open up your computer or whatever device you're using, and then you will just continue with the computerized portion of the exam. You will, of course, do every problem that you get on the exam. You would just do the work on a piece of paper. You input your answers on the computer system, and then you just hand in your work at the end, and then that will be used as partial credit in case you get something wrong. The other thing I wanted to say, I received just a few emails from some students that they suddenly realized that they have to do some exam 1 corrections that they want to be changed. I got your emails and I saw them, but I did not respond to them yet because right now the priority is to actually create this exam. And once the exam is given and all of that is done, then I'll get back to your emails again. The important thing is that you send the email so there's a record of it and there's a record of your work. So as long as we have that, we can always change the grade if there's something to be changed at a future date. But for the time being, I'm not going to answer any emails about regrading questions just yet. because I'm going to be creating the exam. So we'll finish here, and then Thursday, we'll talk about how you can use this knowledge of eigenvalues to then locate these nice bases to work with your linear maps.